Significant figures are the difference between numbers in math and numbers in science. Numbers in math are assumed to be, well, just numbers. Numbers in science can also be numbers, but they can also be measurements. And measurements are fundamentally different from numbers in that they can be exact or they can be just estimates. Here's an example of sets of things that are just numbers. Pi is a number. It's a transcendental number. It can be as exact as the number of decimal places you have on your calculator. 1/2 is a number. You take it and you break it in half. You break it into two equal pieces, and that is that. E is a number. It's not 2.718. It is, as before, however many decimal places you have room with. The 3 in the x to the third is also that, just a number. If you're doing calculus and you have to dot and carry and bring the 3 down, that 3 is 3, T-H-R-E-E. It wasn't measured, it just is. How many x's did you have? You had x to the third. Measurements are exact or estimates or something in between. If you're counting the number of people at a rally or parade, Black Lives Matter, and we've got 500 people willing to march in protest. Did you count every single one of them? No. But, from out the window, from where you were recording, it looked like about 500 people, more or less. If it was a little more, so much the better. If it's a little less, well, we'll do better next time. 2 sig figs, you have to be more exact. If you are setting up chairs for a benefit full of rich people willing to hire lawyers and hire lawmakers to help make Black Lives Matter, you need to be more exact than 500 to the nearest 100 people. If you're setting up chairs, you need to know exactly how many chairs to set up. Now, if you have 525 instead of 520, you'll still mostly be okay. You won't have this huge embarrassing row of empty seats to make people think that your benefit is underattended. And if somebody brings a kid or two and you only have 518, 519 chairs, all right, somebody can sit on their mom's lap. But more or less, you should get about 520 chairs set up. If you're taking tickets, that's 3 sig figs. You didn't sell 520 tickets, you only sold 516. And the chair of the foundation is going to want to account for all of that revenue. If you say 520 when it was only 516, then you're going to need to account for the extra 4 tickets or the $400 that you don't have in your cash box. 4 sig figs, we're no longer counting heads. 4 sig figs is something that we have to measure really, really precisely, like dosage in medicine. The reason you always get weighed when you go to the doctor's office, even when you're going in there for a headache or a broken wrist, is so they can calculate the exact dosage of medicine to give you for your body size and weight. My baby's pediatrician busts out the calculator every single time we go in there and tells me to the nearest 0.1 milligram how much Tylenol I should give the baby. I think I should be flattered that the doctor thinks I have a micropipette at home and I weigh out the baby Tylenol into an eyedropper as if I were in a chemistry lab. Speaking of chemistry labs, we're definitely there in 5 sig figs. It doesn't matter if you're measuring milliliters of dosage or milligrams of anything. If you have something that is toxic before the chemical reaction and harmless after the chemical reaction, you want the exact amount that you need. Any leftovers, and you're going to have toxic residue in a beaker of something you thought was harmless, don't put in enough, and you may not have enough reagent to get the chemical reaction started, or you may have more of one reagent than the other so that you have all sorts of bits left that you didn't plan on, toxic or otherwise. You don't want 520 milligrams. You don't even want 517 milligrams. You want the exact 516.87 milligrams, no more, no less. By the time we get to 6 sig figs, we're breaking out the bomb squad here. But the 6th sig fig, if you really care about it that much, then any leftovers you may have may blow half of us to kingdom come. I can't think of anything in a high school laboratory that's measured to 6 sig figs of precision. If we have university-grade equipment or international standard data for the charge of the electron or the wavelength of the green light in mercury vapor, that's 6 sig fig data. How do you determine the number of sig figs in your data? What you're doing is you're trying to decode how well the scientist did at measuring. Was she a very, very precise scientist, or did she kind of squint at it with one eye and her glasses off and say, yeah, that looks about right? The way we tell is with a decimal place. If there's a decimal place, all zeros are significant, starting with the first counting number. If there's no decimal place, that's scientific code for that was an estimate. I did not measure, I just guessed, so don't take my data too seriously. This was somebody's eyeball estimate. It's a little bit less than 7,100, so that's about 7,090. 3 sig figs. Count them. 1, 2, 3. The 0 on the end is not significant. Now you try. How many sig figs here? Write it down in your notebook. If you got 2, you're in good shape. The 0 on the end is not significant because there is no decimal place. Now how many sig figs here? Write it down. If you said 4, check your answer. There is a decimal place. That means all the zeros are significant. That's 6 sig figs. What about this one? 6 sig figs again. There is a decimal place. All the zeros are significant. What about this one? If you said 4, again, check your rules. We have to start with the first counting number. Not this, not this, not this. We call those place-holding zeros. This says 4 millimeters, or 4 milligrams, or 4 millisomething. The 0.000 is just our way of saying milli with numbers. It tells us how big the measurement is, but not how precisely the scientist measured. This scientist looked at the width and said, yeah, that's about, I would say 4 millimeters, certainly not 5, but didn't actually measure past the first millimeter. This has 4 sig figs. Not these, but these. 5.080 times 10 to the negative 4th. These zeros here at the end are all significant because there is a decimal place. How many sig figs does this have? If you answered 5, then you remembered the rules. If you answered 8, again, you have to start with the first counting number. If you answered 2, remember there is a decimal place. All these zeros on the right are significant. The reason we have these rules is to help us round our final answers to something that's useful, not too vague and general and useless, but not so specific as to simply be a lie. When you're doing physics problems, do everything on your calculator in one large step. The whole equation, you should only be pressing enter once. Having done that, when you have your absolute final answer on the screen, count the sig figs in your problem. If there's a measurement in black ink, find the one with the least number of sig figs and round as your last step. So if this is your calculation, type this exactly as it stands here onto your screen. 1/2, parentheses and all. You don't have to put the kilograms and meters per second and meters in, but type this exactly in and look at your screen. If your screen looks like this, you are in good shape. Press enter. Got the parentheses? Got the squared? Got the 1/2? Cute little mixed fractions, everything look right? Proofread. Make sure you've got your order of operations there. Ready? Enter. Guess what? 1/2 of 510 kilograms times 9.29 meters per second quantity squared divided by 430 meters is not 51.180338 kilogram meters per second. It simply isn't. It's not true. Why? Because whoever measured this 430 did not do so precisely. This was an estimate, and this 510 was an estimate. That wasn't weighed on a chemistry balance. That was eyeballed to the nearest kilogram. For all we know, this could be 509.95, or this could be 434.9999992. And all of those decimal places would change these last 6 trailing digits. They could be a lot more than 0.18. It also could be a lot less. The only truthful thing that we can say with 2 sig figs here and 2 sig figs here is that all told, it's about 51. Maybe a little more than 51, maybe a little less than 51, but we can't truthfully say that it's 51.1 or 51.2. For all we know, it could be 51.4, it could be 50.786. What about this 1/2? Doesn't this have 1 sig fig here and 1 sig fig here? No. Half, as I said before, is cut it into 2 equal pieces. This was not a measurement, it was a pure number. Those numbers don't have sig figs. The rules are almost the same for adding and subtracting. Do the whole thing on your calculator in one large step. Do all the addition and subtraction together. When you're done, round your final answer to the least number of decimal places. For instance, if you're trying to find the total energy intake, if you had 13 calories, 921 calories, and 100 calories, that's not, strictly speaking, 1,034 calories. Certainly not if you're a scientist. Why not? Check the number of sig figs. What's the smallest number of sig figs you see there? If you said only 1, you're in good shape. This 100 calories was not measured, it was guessed. It was about 100. For all you know, it could be anything over 50 and under 150. It's measured to the nearest 100 calories. It could be a lot more than 1,034, it could be a lot less. In this case, all we could really say is that it's somewhere in the thousands. How do we do decimal places? This doesn't have any decimal places, this doesn't have any decimal places, this doesn't have any decimal places, so how can we round to the nearest number of decimal places? When we say decimal places, we are assuming that you wrote the whole problem in scientific notation, whereby this has 1 decimal place, this has 2, this has none at all. Our answer should have no decimal places and should be, as we guessed it would be, about 1,000 calories. I'm writing the words out to show you what an estimate this is. Moral of the story, always take more than 1 sig fig, and when you can, take more than 1 decimal place. Now you see why it is that we use scientific notation. Scientific notation has 1 digit to the left of a decimal place and helps you keep track of those bazillion zeros knocking around. In English, we like to do this with commas, but that's only North America. Go to Latin America, go to Europe even, and you will see as right here the comma that we thought was a thousands marker serving as a decimal place, and the period that we thought was a decimal place serving as a thousands marker. Scientific notation helps us be absolutely certain what we're reading from one country to another. Ask Victor, ask Fede, ask Daphna. Scientific notation is the only portable way to go. Your calculator has a special key for scientific notation. It's a capital E, it's very small, and it's doubled up. Do not write times 10 to the whatever power it is on your calculator. Your calculator will not understand, it will trip over its own order of operations, and more often than not, you will type the right problem, but get the wrong answer, especially in a denominator. Use that E key. To write a problem in scientific notation, move the decimal place left. Start with the decimal place where it is for a big number. Move it the appropriate number of spaces to the left. There it is. That was 9 spaces. That's 8.99 times 10 to the 9th. Coulomb's constant of static electricity. For a small number, start the decimal place where it will be and move it left. In this case, that's 6 spaces. That's 9 times 10 to the negative 6th. That is the size of the Schwarzschild radius to make the Earth a black hole. Take it away in scientific notation.